All right, so we are going to get started into chapter 4 today. And with chapter 4, we are talking about atoms and elements. And so we have touched on some of these concepts already in kind of pieces and parts, but we're going to hit them a little bit more in detail this week. So we want to kind of start with the basics, going back to when was the first real mention of atoms and what did that atomic theory look like at the time? And so the first discussion of atoms goes all the way back to 5th century BC, 4th century BC. Democritus and Leucippus, two philosophers of Greek origin, are the first, at least credited, with recording this idea of atoms. And their concept of atoms were pretty simple. At some point, you are going to be unable to divide matter into any further degree than what you do right now. So I can take this piece of paper, and I can rip it apart, and rip it apart, and rip it apart. But at some level, I'm going to get to some point where I'm going to be unable to rip apart the pieces that make up this paper. So that was the concept of atoms to Democritus and Leucippus. You've got these tiny indestructible particles that at some point after you break down matter enough, you're going to get to this part that you cannot break down any further. The word atom comes from the Greek word atomos, which is what Democritus called these particles that you could not break, because atomos is literally the Greek word that means indivisible. So unable to be divided further. So that is our earliest origin of atomic theory. If we skip forward a little bit more, so we skip from 5th century BC to 19th century AD. Now, that's not to say that there wasn't something going on in those 2,400 years in between. There was. But for the most part, it largely involved just kind of going back and forth between whether or not atoms were actually indivisible or not. But we come to the 1800s, and we encounter a scientist by the name of John Dalton. And John Dalton develops a theory of atoms that gains some wide existence and wide acceptance to the point where we still talk about it today. Overall, there are 3 parts to Dalton's atomic theory. First, we understand that every element is made up of these indestructible particles that we call atoms. So here comes in the integration of Democritus's atomic theory into Dalton's atomic theory. Only thing that Dalton does is he specifies that that particular thing, that atom, has to be associated with an element and not something like a compound. We have a different name for those indestructible building blocks of compounds. We call those molecules. The second piece of Dalton's atomic theory concerns elements. All atoms of a given element have the same mass. And they also have other properties that would distinguish them from atoms of other elements. Now, this particular part of the atomic theory is one that's not going to stand up completely as technology comes by. But for his time, it did a pretty good job. We know that all atoms of a given element have something fundamentally the same about all of them. We know atoms of different elements have something fundamentally different about each of them. We'll get into what those similarities and differences are here in a minute. The third thing that Dalton's atomic theory touches on is the idea that when atoms combine, they are always going to combine into these whole number ratios. And when those ratios are fixed, that's what we know as compounds. So a compound is simply a combination, a whole number combination of multiple atoms, multiple elements together in some kind of a fixed ratio to generate this molecule. And for about 100 years, Dalton's atomic theory is largely going to stand up. And even after some of these early 20th century discoveries, we're still going to find that this largely kind of holds true. But there are some technological advances that do take place in the early 20th century that do a lot to help drive forward atomic theory. One of them is that somewhere along the way, we discover the electron. Now, J.J. Thomson is most commonly credited with the discovery of the electron. There were a lot of other scientists working at that time doing the same thing. What stands Thomson out from the others is that he was able to better quantify it than others. He was able to calculate the charge. He was able to, or at least calculate something called the charge to mass ratio. He was able to determine that electrons were negatively charged and discover some of the other properties of electrons. Namely, those electrons are tiny, tinier than the atom itself. They actually come from the atom itself. And they are considerably smaller and lighter than the atoms themselves. But he found that these electrons were present in lots of different things. So the experiment that he used was something called a cathode ray tube. And basically what he found is that when he put different materials on the end of that cathode ray tube, he always was able to generate electrons. So it doesn't matter if the sample was metallic, non-metallic, you name it. He was able to generate these electrons from it. And so that's how he concluded that the electrons were in all things. Now, based upon his findings and what he knew at the time, he developed a model of the atom that was called the plum pudding model. Now, as Americans, especially 21st century Americans, we don't have a whole lot of context for what plum pudding actually is. In, I guess, the easiest terms I can think of, when Brits call something a pudding, they are usually referring to a cake of sorts. Plum pudding would be a plum cake that was usually kind of like a fruit cake, and it had different bits of fruit into the cake itself. So the plum pudding model talked about the atom as being kind of like this cake substance that had all these different fruits dotted in it, raisins, and the raisins were representing electrons. So we see this a lot as we kind of talk about the scientific method. How do I take information that I know, things that I've discovered, and put it into a way that's familiar for me to try to explain? And so that's what this model is. The model is taking this idea, hey, people know what plum pudding is. Let me try to explain what an atom looks like in the terms of this common dessert. To us now, doesn't make as much sense, but luckily this model didn't last very long because things got better. Another classic experiment, the gold foil experiment of Ernst Rutherford. What happened in this experiment was we had a radioactive material here that shot these radioactive bits, alpha particles. Now, alpha particles themselves are relatively heavy as far as nuclear material goes. So an alpha particle would be somewhere around 7,500 times heavier than an electron. So we're talking about it's got some significant mass compared to what we were seeing in the cathode rays. Now, when he shot this beam of alpha particles at this very thin piece of gold foil, what he discovered is that most of the particles actually passed through the foil. And that's actually kind of what he expected. After all, with the plum pudding model, if I am shooting these high energy, heavy objects into this kind of spongy matrix that we're calling an atom, I'd expect that those heavy objects would just punch right through them. And for the most part, they did. But the problem was they didn't all do that. Some of them were deflected off by just little bits. Some were deflected by very large angles. And so that told Rutherford, hold on a second, plum pudding model says something completely different than this. Here's what I would have expected in the plum pudding model. Alpha particles just getting shot through that plum pudding, very minimal deflection at best. Instead, we got something completely different. Now, from a nuclear perspective, I want you to think about this. Put an answer in kind of on the quicker side here. Compare the expectation to the reality. Expectation, those nuclear bits, those alpha particles are supposed to punch right through that plum pudding and come out on the other side virtually unchanged. And while most of them did, some of them did get smacked off at slight angles. Some got smacked off at big angles. Give me a brief explanation why. And if you don't know, that's okay. Try to think it through here. That's perfectly okay. It's perfectly okay not to know. The reason I'm asking the question is not because I expect you to know it, but I'm looking to see if you're thinking. So give you a few more seconds to put something in. Right. So I'm going to focus on one answer. And I won't say whose it is because I don't know. It doesn't really matter. But here's pretty close to what the correct answer is. If I've got this dense nucleus at the center, if I've got this hard object that I'm shooting these alpha particles at, if they actually hit the nucleus, they're going to bounce. Because the nucleus, we're talking about gold here. Molar mass of gold is about 197. And even though an alpha particle is a lot heavier than an electron, its molar mass is actually only about 4. So I got this big center that I'm shooting these alpha particles at. If they actually hit the nucleus, they're going to deflect. And they're going to deflect hard, depending upon how hard, at what angle they actually hit them. So if they just glance off the top of that nucleus, they're going to shoot off just a little bit. They hit that nucleus head on, they're going to deflect at an equally just angle. So the overall takeaways, we know we end up getting something from this called the nuclear model of the atom. The nuclear model of the atom is largely the model that we are working off of even to today. But in this nuclear model, we've got this nucleus in the middle. The nucleus contains the majority of the mass. And surrounding that nucleus, we've got all of those electrons. And while the electrons don't have a whole lot of mass, they do take up a lot of space. And so that explains why the gold foil experiment went the way that it did. Why did most of the alpha particles pass through? Well, because most of this space is just electrons. So if I take that alpha particle and I have it encounter a grain of rice, it's not going to be moved by the grain of rice. But if it hits that nucleus, it's going to be moved straight by that nucleus. Right. Give me one piece of data on the way out of here. And once you fill this out, you're free to go. Have a great afternoon. We'll talk more about the nucleus and what goes into it on Wednesday.